And how is my sound, by the way? Is my audio sound okay to you?
Yeah, it sounds okay. It's very clear. It's very good.
Okay.
Okay. Well, let's start. People are still joining us, but it's better to start for those that are on time. I'll do a short introduction and then I will pass you the floor, okay? All right, thank you. And let me start recording also before I forget. Okay. So hello everyone and welcome to another talk in our webinar series. This webinar is also being streamed live on YouTube. You can find the link on our website or access it on our YouTube channel, LIneA MCTI. Today we have the pleasure of having Dr. Kyle Dawson, Professor of Physics and Astronomy at University of Utah. He was the principal investigator for the extended Baryon Oscillation Spectroscopic Survey and now is the co-spokesperson for the Dark Energy Spectroscopic Instrument, or DESI. His research is very broad and passes through many fields of study, focusing now on baryonic acoustic oscillations, but also have been working with supernova cosmology, great galaxy clusters, the development of charge coupled devices, to name a few. Without further ado, and hoping that those brief words have done a little justice to all your hard work, I'd like now to hand over the floor. Kyle, if I may, thank you very much for being with us today, and the floor is yours.
Okay, great. That was very nice. Thank you so much for that introduction. I'm going to share my screen.
Okay. Okay, we can see it. Let me just remind everyone that if you want to ask questions during the presentation, please put your questions in this chat. Kai will be happy answering it during the presentation, okay?
Yeah, exactly. I'm happy to be interrupted. I often find the interruptions make it a little bit more engaging, so please do. Okay, so again, thank you so much for the introduction. That was very nice. I'm going to give a presentation describing the cosmology that we learned from 20 years of spectroscopic surveys at the Apache Point Observatory, the most recent of which is called the Extended Baryon Oscillation Spectroscopic Survey, or EBOS for short. Okay, so in the outline of my presentation, I'm going to just give a quick background of cosmology. I know that there's a breadth of background in this audience, so I'm going to go through it really quickly. Hopefully people have already heard of concepts like baryon acoustic oscillations or redshift space distortions. Those are the two tools we use to measure the cosmic distance scale and the growth of structure. So our sample completed, our program completed in 2019. The results I'm going to show we released about a year and a half ago. Okay. So starting at the very, very high level, when we talk about cosmology, we talk about understanding the broad model that explains all the physics in the universe. And as we've done so, we've learned a lot about the acceleration of the universe, things like dark energy. And at the same time, we've also started to see hints of confusion or tension in those measurements. So if you look at different probes, they all have different access to the cosmological model. And sometimes probes don't give consistent results. So there's really, in the last few years, 3 different regimes where this has come up. I highlight each of those 3 regimes here. The first is if you look at the Planck CMB data alone, there's some evidence that maybe the universe is far more curved. It has a much larger curvature than one would expect from inflationary models. That is one point of curiosity. Another is the Hubble parameter, the H0, measured today, the Hubble constant. If you measure it different ways, you get very different results. I'm going to spend a fair amount of time talking about that. That, in my opinion, is probably the most compelling tension that we've seen recently in cosmology. And the third is in the growth of structure. How has the matter accumulated under the force of gravity since the cosmic microwave background? And are the results consistent with what you'd expect in general relativity? And we're seeing hints of tension there, although not as significant as you're seeing in the H0, the Hubble constant regime. Okay. Now, all this comes back to the general cosmological model. There's really two different ways that we look at cosmology. One is the derived measurements in the expansion history, cosmic expansion, and BAO and spectroscopic survey measurements. Those two measurements are h of z and dm. That's the angular diameter distance. So those are basically just distance measurements. The other tool we have at our disposal is growth of structure. In terms of the spectroscopic survey, the direct observable is called F sigma 8. And that's just a measure at each redshift interval of how quickly structure is growing relative to its amplitude at that time. So if you make these measurements, you can constrain the cosmological model, you can get the physics of dark energy, you can get the composition of the universe. You can also get particle physics like the mass of the neutrino. You can get early universe physics like the properties of inflation, and also test general relativity. The basic idea here is I have a box on my left, that's the observable universe, and I compress that into a cosmological model with all of the parameters here on the right. Okay. Well, I'm not going to go into this in detail. But the tool we have to describe the expansion history is primarily the Friedman equation. It's just like an equation of motion for space. It relates on the left-hand side, this h of a term, that's the Hubble parameter, to what's happening on the right-hand side, which is the composition of the universe. And there's lots of ways I can parameterize the composition of the universe. This k c squared over a squared, that tells you what's the geometry, what's the shape of the universe, what's its curvature. And here on the left-hand side, this rho term is just what is the composition. And there's lots of ways, composition is dark matter, baryonic matter, neutrinos, photons, and also dark energy. Okay, and dark energy, we don't know what it is, so we allow pretty flexible parameterization of dark energy that also goes into this Friedman equation. Okay, the parameterization allows the dark energy density to evolve in different ways as the redshift expands. So we call that the equation of state for dark energy. So the Friedman equation is all about the expansion history of the universe. The direct observables in spectroscopic surveys stem from what's called the Baryon acoustic oscillation feature. Here is an artist's conception of that feature in the distribution of galaxies. You can see this ringing of overdense regions around each central galaxy. This is exaggerated for effect. It's a much weaker signal than what you're seeing here. But the basic idea is this ring has a scale or a size that's determined in fairly early times in the universe. And if I can measure this in the distribution of galaxies at any given redshift, I can use it as a standard ruler. And I can use it as a standard ruler in two dimensions. If I look along the line of sight, right, I get an observable, which is the delta, the difference in redshift between the front of the ring and the back of the ring relative to its distance. That is a measurement of the Hubble parameter. So like the velocity difference is on the separation and it's relative to a distance. So you get something that looks like a Hubble parameter. If you measure it transverse to the line of sight, because this ring is a sphere, really, it's a spherical overdensity projected into a plane that looks like a ring. But if you look at it transverse to the line of sight, you now can make an angular diameter distance. It's just triangulation. If I know its diameter and I measure its angle, by geometric effects, I can determine the distance to it. So I get those key measurements that go into that Friedman equation, okay? On the growth side, just like the Friedman equation relates to it's like an equation of motion for the universe, the growth function tells you how matter accretes over time under the influence of gravity. So you have this growth factor, it's an overdensity, it's called delta at any given position, and it grows such that at any given redshift or given time, it's increased in amplitude by a factor big D. That is the growth factor, okay? I can solve for big D under the law of general relativity. That's the growth equation. I don't want to worry about this in too much detail, but just look at the parameters in it, okay? It has a growth factor, big D. It has an h of z term, so it depends also on the expansion history of the universe. So it's going to relate growth to expansion history, and then the other term in here is omega matter, which tells you what fraction of the universe is made up of things like baryons and dark matter. Okay, so those are the parameters. If I can measure something for this D term, this big D, I can then start getting constraints on h of z and omega matter. Now, this linear growth rate is what I actually measure. What I measure in spectroscopic clustering is what's called F sigma 8. It's measured through redshift space distortions. And F is effectively the derivative of this D term. It's basically this D dot term here in the growth equation. But you don't measure it alone. You measure the relationship between the growth rate at any given redshift and the amplitude of clustering, which is the sigma 8 term, okay? So you measure that by looking at the ratio of what's called the monopole here in blue. That's the monopole in the clustering signal relative to what's in orange is the quadrupole. That ratio tells me how much my matter is infalling into a gravitational potential basically at any given redshift. That's a simple way of looking at it. Okay. So those are the parameters I want to derive from a spectroscopic survey. I have to have a direct tracer to actually observe. We choose tracers from imaging data based on how easily you can determine the redshift and number density for a given selection, okay? So you take optical imaging data in multiple band passes, and over a certain redshift range, you draw cuts in color and magnitude, and you get a sample that you then apply for spectroscopy. We use galaxies out to a look back time of about 6 or 7 billion years ago. At larger distances, we use quasars because they're brighter and they're easier to see when they're further away. So we have a different selection algorithm for each redshift interval. This is what the distribution looks like for BOSS and eBOSS. It's orange is galaxies, red is quasars. And then back to a look back time about 13.8 billion years ago, you have the CMB, which is not one of our observables, but it is a big observable for things like Planck. Another observable that's a little bit more subtle is not the direct beacons out there that are mapping out where there's matter, but rather using a beacon in the background and illuminating all the foreground material. And you can map out all the foreground material and make a three-dimensional map from the absorption in that background source. So the background source that we use are quasars, and the absorption is caused by neutral hydrogen, which leads to what's called the Lambda forest. This is another technique, okay? That gives you access to the highest redshifts 2 to 4 in our samples, okay? So I was really involved with 2 different projects to make three-dimensional measurements of the matter distribution using these techniques. The first was called BOSS, this one called eBOSS. Here's the basic outline of how we run an experiment in three-dimensional spectroscopic surveys. Up in the top right-hand corner, we start with imaging data and all of its glory. It's beautiful stars and galaxies here in these little dots. In all its ugliness with saturated stars, diffraction spikes, we got to fold it all in and figure out what's real and what's not real. We make observations of objects that we think are real. That's here in the middle panel with our telescope. We get redshifts, or we get spectra of each object. We get about, in BOSS and eBOSS, we got 1,000 spectra at a time. Each integration time was roughly an hour and a half. Okay. These are what those spectra look like for galaxies up in the top, quasars in the bottom panels. Once you get spectra, you can classify them with an automated pipeline. You get three-dimensional locations. The two-dimensional location is where it appeared in the image, right ascension declination. The third dimension is its redshift. Now you have a three-dimensional map. You can look for the structure in that three-dimensional map here. This is a numerical simulation, and deduce the cosmological model, okay? When you look at the process, we worked on this for 20 years. It actually started in SDSS before I was even a graduate student. And before I was in spectroscopic surveys, I started out in CMB observations. So in 20 years, we've really learned a lot. I think we really have an excellent understanding of all the parameters, all the steps in that model to get out the final results. We understand the selection functions, how it works, the imaging limits. We understand how to run the telescope. We had less than 1% downtime. We were turning cartridges over as quickly as we could. We understand how to take the exposure so we get uniform coverage of the sky. We spent years optimizing the data reduction pipeline to get optimal reductions, optimal redshift classifications, all the way down to very, very low solenoid data, where it's very hard to distinguish between signal and sky and garbage. At the end of the day, we are working at better than 90% redshift efficiency, even for the faintest targets. And from those data and all those steps, we could create catalogs of the three-dimensional clustering that take into account where we have uncertainties in imaging data, where we have uncertainties in redshift success rate, and fold all those into the analysis. So it's a lot of work, and I think we really did a great job hammering out those details. The samples we used cover, as I showed earlier, a large redshift range. They just have different names, different selections: low Z, CMAS, or galaxies; Lyman alpha, or quasars; LRG, ELG, or galaxies. Each sample was tuned to a different redshift range. And when you look at the three-dimensional map, you see how each of those samples represented in a different color represents a different coverage in the universe, different coverage and distance or redshift, okay? So that was a time sequence of how we took those data. Now you see the 6 different samples we used in different color schemes. Look at them in 3 dimensions. And as you zoom in, you can really see the individual footprints of each survey. And when you get to the highest density regions here in green, that's the Sloan Digital Sky Survey data. You can even see the filamentary structure from large scale structure. This is all real data. This is a real presentation in 3 dimensions, all drawn to scale in co-moving distance relative to the cosmic microwave background. That outer sphere you're seeing is the cosmic microwave background. And lots of other things you can look at YouTube later. Okay, so now we have our 3-dimensional map. We understand it. We measure the RSD and BAO from those maps. That includes things like systematic errors. We use a lot of high fidelity simulations to do that. There's many papers describing the process. At the end of the day, what we find with all our theoretical modeling, tests on synthetic data, that we measure things that are really dominated by the statistical errors or the statistical power of the data. We're not limited by modeling artifacts. Okay, that's the end of the story there. We take multiple measurements of each sample. We measure the 3 things: the BAO along the line of sight, that's H of Z; the BAO perpendicular line of sight, that's DA or DM; and F sigma 8, which is the growth of structure term. We can measure it multiple ways. We can measure it by looking in real space. We call it the correlation function. We can measure it in Fourier space. We call it the power spectrum. There are different techniques. They're highly correlated because they're from the same data sample, but we can use mocks to calibrate how everything lines up and find a consensus between multiple measurements. And here in black is the examples from one of our samples. It's a luminous red galaxy sample. And you see in black the contours on alpha parallel, that's BAO along the line of sight. That's the H of Z measurement. Alpha perpendicular, that's perpendicular line of sight. And F sigma 8, that's the growth of structure term. Okay. You can see they're fairly precise measurements with some degeneracy between them, particularly between F sigma 8 and the BAO parameters. Okay. Here's what those measurements look like in all of our samples. This is a presentation on a Hubble diagram. This is normalized to what you would expect if the measurements were exactly aligned with the Lambda Cdm cosmology as predicted by Planck. That's the dashed line here. This is literally the BAO measurements we made in each bin. Here at our lowest redshift sample, that's from SDSS. Here in our moderate redshift sample, that's from BOSS. Here and here, it says BOSS LRG, BOSS LRG. BOSS and eBOSS, that's from our eBOSS sample combined with a high redshift tail of BOSS. eBOSS emission line galaxies, eBOSS quasars, and BOSS and eBOSS Lyman alpha forests. So all the techniques. And what you see here is a very large redshift range. We go from redshift 0 to redshift 2.5. Making these measurements of the distance redshift relationship. We do the same thing with growth of structure measurements, except we're not able yet to do these measurements with the Lyman alpha forest. We can only do growth of structure measurements when we have direct tracers. We are unable to model a Lyman alpha forest for multiple reasons. We're working on it, and we think we can do so in the future. But what you see here is the two-dimensional correlation functions from these different clustering samples. Again, here there are 6 different samples. The direction along the y-axis is the amplitude of clustering along the line of sight. The structure on the x-axis is the amplitude of clustering perpendicular line of sight. And of course, the separation is represented as the distance along the x or y-axis. What you see, especially if you look at this BOSS DR12 middle redshift bin, is if I look, it's squashed. So the shape is not spherical now. The density, the clustering is squashed, and that's the measurement we're making. That's where we see a difference between the monopole and the quadrupole of the distribution. And that's the growth of structure. That's a measure of the rate of infall of matter into its gravitational potential. Okay, the amount of squashing relates the infall rate to the amplitude of the gravitational potential. Okay. When you look at all those results on the expansion history side, okay, at low redshifts, we can measure the aggregate expansion history between redshift 0 and 1 at 0.7% precision. So these are very highly precise measurements now. At redshifts higher than 1, you measure it at 1.2% precision. Okay, that is really exceptional. And particularly in that redshift range above redshift 1, these techniques are quite unique. Meanwhile, all those growth measurements, the F sigma 8, the aggregate precision is about 5% over the full redshift range covered. And here's a link that summarizes all these measurements. We put this together at the conclusion of eBOSS, and I think it is an excellent way of understanding what we produced over the course of the survey. Okay, now, this is the meat of the talk, and is what I really want to focus on. I can take a break for questions about how we get the measurements. What are the observables in the data? Does anybody have any questions to the chat window or through raising your hand? Okay. Feel free again to interrupt as we go on. That was a nice stopping point. So now that we have these BAO and RST measurements, the rest of the talk is going to be about what we learned about the cosmological model from those data. We completed this result in the middle of 2020. Then we all went into our holes from COVID, and now we're climbing out. So here I am to present. That in 2020, we had 23 papers, but we all released together describing the whole process of making these measurements. This paper here was a collaboration paper describing the cosmological interpretation. It's alphabetical ordered. I want to make a special call out to the people who really helped lead that paper, which is always hard to understand when it's an alphabetical paper. So Eva Muller, Andrea Font-Ribera, Andres Lozar, and my colleague here, Zhang Zhang, and then myself were the people who really led the interpretation of the data. And that's what we're going to see from here on out. Okay. So how do we want to look at this final interpretation? We wanted to make two statements. First, this was a really big milestone in cosmology. With the conclusion of EVOS, it was the conclusion of stage 3 spectroscopic surveys for dark energy. That was a 10-year milestone. It was on the scale of the decade, so it ended around 2020. It was the largest sample ever obtained of spectroscopic galaxies, over 4 million spectra. It sampled a larger redshift range than any cosmological probe. It gave percent level precision BAO measurements and 5% level growth measurements. So very, very distinct, very powerful. Let's talk about the legacy of those data. And we talk about the legacy in the context of 5 cosmological questions. They also kind of pertain to what I introduced at the beginning of the tensions we were seeing. What are the big questions about growth of, sigma 8 and Hubble constant? So the first is the BAO are so precise. What do we learn about dark energy and curvature? What do these expansion history measurements give us for dark energy and curvature? Second, what do they tell us about the H-naught tension? We often see CMB H-naught measurements versus supernova H-naught measurements. Where did BAO fold into the story? Third, separate from BAO, what can we learn from the growth alone? Growth of structure has always been highlighted as a significant tool for measuring the cosmological model. What did we actually learn from doing these measurements? The fourth, which I'm going to have to skip for time, is bounds on the neutrino mass. I've always found this to be very interesting. We see neutrino mass constraints from particle physics experiments, but the reality is we actually, in absolute terms, do a much better job in cosmology and constraining the neutrino mass than anything in particle physics. And it's almost like an order of magnitude. It's a significant difference. And I think the last bullet point is the legacy question. How do you present holistically how we advance the cosmological model as we progress from stage 2 to stage 3 in cosmology? So basically, what did the 2010s decade give us for the cosmological model? Okay, so as we talk about this, I just want to step back to the cosmological model. Our standard model is called the Lambda Cdm Cosmology, where you have cold dark matter. This is a flat universe, curvature equal to 0, and a cosmologist constant that describes dark energy. That's the lambda thing, okay? I can then look at extensions to that model that are more flexible to describe either the expansion history or the growth of structure. And the primary parameters we use to extend the model are first, omega k, that's the curvature. That's if I draw a triangle in space, do the angles that have to be 180 degrees. The second is dark energy equation state, W or W naught. Okay, W naught tells you how dark energy density changes with redshift. Okay, or it also tells you how the matter density relates to the pressure of dark energy. If it's just W, it's a constant. If I allow it to change with redshift, I allow a time derivative, I call that parameter WA. So that's another extension. That's a third parameter I can include. And the fourth parameter I can include is the sum of neutrino masses. That's sum m nu. That is the sum of the 3 mass eigenstates of the neutrinos. Okay, those all affect the expansion history. They affect the growth history, and they also affect the shape of the power spectrum, at least in the case of neutrino masses. Okay, so now let's step through these, starting with the role of BAO for constraining the expansion history. it's really illustrative to see how different observables relate to the models you're constraining in your extended cosmology, in your extensions to Lambda CDM. So here I show that on the top panel, it's what do you learn if you make angular diameter distance measurements? That's BAO perpendicular. The second is what if I make H of Z measurements? And the bottom is what happens if I make luminosity distance measurements? Those are what come from supernova, type 1a supernova. Note that the BAO are also measured at redshift of 1,000 from the CMB. You get an angular diameter distance there. So you have a super long baseline, and that's a very powerful tool. Because the BAO are coupled to that CMB, you can highly constrain perturbations to the Lambda CDM model that are resulting from opening up the equation of state for dark energy. That's the green, this WCDM. From changing the curvature, that's the red. Or by adding a free neutrino mass, that's the blue. And this red and green, those are actually the preferred central values. That's the expansion history you expect, using the preferred central values from Planck without any additional information. So you can see right away, Planck had this controversy about indicating possible curvature. The curvature from the central value of Planck is off by, it would be predicting 20% differences at redshift 0 than what we see with BAO measurements. So you can see that power of the BAO measurements relative to Planck, when you combine with Planck. Okay, that's a nice illustration here. Supernova actually do a great job at low redshift. The error bars are much smaller around Z of 0 than they are in the BAO terms. So they're a very powerful probe when you see big changes between redshift 0 and 0.5. The biggest change here is the green curve. That's the dark energy equation of state. So we'll see later that supernova do a great job for getting the dark energy equation of state. And that's the reason why. Okay. Now, this is the parameter space that was used in supernova. It was a Lambda CDM model with one free parameter allowing curvature to float. And you can look at the energy density of dark energy relative to matter. This is what the supernova measurements used that led to the Nobel Prize. These is now updates to those original measurements with the CMB Planck measurements in gray, the supernova from the most recent sample called the Pantheon sample in red, and the BAO in blue. The dashed line is what you expect from a Lambda CDM model with 0 curvature. And what you see is that both the red and the blue prefer that model. You can see that the error bars are actually smaller on the BAO measurements than on the supernova when you allow curvature as a free parameter. You can also see that they're both nicely perpendicular to the CMB measurements. Now on the right hand, we take the same model, we just rotate the parameters. So now instead of omega lambda and omega matter on your x-axis and y-axis, you now have omega curvature and omega matter. So you've just flipped the y-axis to omega curvature instead of omega lambda. And here you see that controversial measurement from Planck, where you have a preferred value of curvature that's very negative. But you also see huge error bars and a very large degeneracy with omega matter. Omega matter values were allowed between 0.3 and 0.6. When I add in the blue, okay, the blue is now adding the BAO measurements just to those Planck. And look at how the contours shrink up. That's because you now have that long baseline and redshift coverage, and you really exclude that high curvature parameter space, and you decrease the error bars by about a factor of 10. It's a huge improvement. It's a order of magnitude change when you add BAO. And Planck is extremely precise, but you don't have that redshift lever. Okay. You also now are within an order of magnitude of the cosmic variance limit of curvature measurements, which is also very impressive. We only have one universe to work with. So at some point, our universe is one realization of a density field, and that becomes degenerate with curvature measurements. And you can't actually do better than a certain limit. And we're within a factor of 10 of that limit. So when you see this, it really makes you question this big press, a lot of the attention that was played about a few years ago into measurements from Planck that ended a possible crisis for cosmology. So I wouldn't call it a crisis until you get this additional information from other probes. Okay. Now you can do the same thing by opening up the equation of state for dark energy. You see that the error bars are comparable for BAO and supernova, BAO in blue and the supernova in red. But there's a nice subtlety here in the supernova because it's so strongly constrained at that low redshift, and because BA and CMB is so highly constrained at high redshift, the two contours of being were really perpendicular to each other, and they're a great complement to each other, more so than the BAO. So you actually get tighter constraints when you combine CMB and supernova on equation state parameters for dark energy. Okay, that's shown here in this table. I don't want to show all of it. I'll just highlight two things that, again, CMB alone, highlighted here in pink. If you allow curvature to float as a parameter in thy first term, or dark energy equation state as a second term, you get big changes. First of all, you have this non-zero curvature here, but you also get an H naught that's 54 kilometers per second per megaparsec. So you also get a very low prediction for the amount of dark energy. So these are kind of warning signs that maybe this curvature constraint, again, shouldn't be taken so literally. Maybe there's something else in the shape of the power spectrum. There's some very large degeneracies at play. And the same thing happens when you open up equation state for dark energy as a free parameter. Look what happens to H naught. In curvature, H naught, if I have CMB only measurements with curvature free parameter, it gets a 54 kilometers per second 54 value of H naught. If I now allow W as a free parameter, I get something exceeding 82, a huge value of H naught. So these are not, your H naught terms vary when you use CMB only data, depending on what knob you're turning in your expansion history, if it's curvature or if it's equation state of dark energy. Okay, so let's look at that in a little bit more detail. Okay, so let's look at what BAO tell us about the H naught tension. To remind everybody, if I make a BAO measurement to an overdensity at a fixed scale, if I don't know that fixed scale, I can just see how that bump evolves with redshift, and I can see relative measurements of the expansion history. Okay, that's if I combine the BAO measurements with some physics from the early universe, I can get a measurement of what that bump scale is in real units of real megaparsecs. And now it's no longer a relative measurement, right? H of Z here is a relative measurement by itself. If I can get RD, the distance of that bump in co-moving units, okay, I can now get an absolute value of H of Z in real units of megaparsec, or sorry, kilometer per second per megaparsec, okay? If I need to know RD. So RD is easily predicted from early universe physics. It's just fluid dynamics. You have photons and you have baryons, and they're shuffling around with each other, and they're creating sound waves. And those sound waves travel at a speed CS that depends on the density of baryons. They are traveling through a universe that's expanding, H of Z, at a rate H that's determined by the matter content and the radiation content of the universe at that time. And it goes on until the baryons and photons decouple from each other. Basically, that's roughly speaking what this drag epoch Z is. That's all fluid physics, all easy physics. And it only depends on omega matter, omega baryon, and the CMB temperature. If I know those three things, I can predict RD, and I can get absolute distances, absolute measurements of H naught. Okay, now look what happens when we do that. On the left-hand side, I show in blue the constraints on Hubble constant H naught on the y-axis for different, for a model that has a fixed expansion history to a Lambda Cdm model. Okay, very tight constraints. In the red is what happens when I use the CMB, BAO, and supernova data to simultaneously constrain H naught and the expansion history in the universe. I allow a very flexible expansion history. And the error bars on H0 don't actually inflate that much. So I'm no longer having the same problem I had when I was opening up the expansion history with the CMB data. I'm not changing the central value. Here in the table, only Lambda Cdm of 67 at 1% precision. But meanwhile, if I open up the expansion history on the CMB data only, I got crazy. I started getting very unphysical values of H0. So the BAO data allow you to be very flexible in the HOD in the expansion history and still get an H0 measurement at redshift 0 at 1% precision. Okay, that's a really key thing. It's not possible without the BAO data. They couple the low redshift to the high redshift and allow me to interpolate over the expansion history. You can also do this measurement using only BAO data and Big Bang nucleus synthesis. You can just completely drop the CMB from the picture altogether. The BBM gives you that baryon density. You can then determine R sub D from early universe physics, and you get the blue contours. This is under a Lambda Cdm model of our BAO measurements over all redshifts in combination with omega baryon from Big Bang nucleus synthesis. It's yet again, roughly speaking, 1% measurement with the same central value. So no matter how I make the changes here, it's extremely robust. The BAO technique gives me a measurement of H0 around 67 to 68 kilometers per second per megaparsec. Okay, and it's really the BAO data. This is that allow it. Now, now we accept there's a tension. You get H0 of 68 when you use the early universe model. You get an H0 of 73 when you do Cepheid and supernova measurements, as in the SHOES project. They're 10% different. One can say, okay, they give different measurements of H0. That doesn't make any sense. H0 is H0. It's the expansion history. It's the expansion rate today. If that's the case, that might mean, if we really take the H0 measurement literally from the early universe physics, I think that probably means that it's measurement error in the other technique, in the local technique. Okay, because it's not measurement error in the BAO, CMB, R sub D technique. It's definitely not. They all give the same result no matter what happens. On the other hand, one can look at this in a different way, right? The BAO here in blue cannot differentiate between R sub D and H0 by themselves. You only differentiate when you add in some other technique. Okay, so you can say H0 is what it is. You can combine in here in pink the supernova and Cepheid data with the BAO data, calibrate your R sub D, and you get something like 135 megaparsec. That's a very different R sub D than is implied by the early universe physics model. Okay, this would not be, okay, if you do it this way, this is not a model dependent statement. This is literally just taking H0 as a way of calibrating my standard distance ruler in the BAO and getting an R sub D measurement out. There's no physics. It's just geometry arguments. That would indicate that maybe there's some early universe physics that leads me to the wrong conclusion of R sub D and the other technique. And that's a very exciting idea, okay? So that's where we are on H0. Let's talk about what we'll learn from growth measurements. And I'll go through this pretty quickly because time is of the essence. Okay, so first, growth measurements, we can show the same plane as kind of like a Hubble diagram as we showed with BAO and supernova. Here, instead of the expansion history estimate on my y-axis, is now the growth measurement, normalized to Lambda Cdm values. What you really see is the black data points are measurements from BOSS and eBOSS. It's very hard to measure things like curvature, that's in the red, but it's very easy now to measure things like W, constant equation state. That's, again, the central value preferred by Planck. You can see the growth measurements alone are going to exclude that. And we'll see that on the next slide. Comparing now our growth measurements with weak lensing as a tool for measuring growth. On the left-hand side, you see if you float curvature as a free parameter, it's really the red curve that shrinks the contour area. And that red curve is what results from getting the weak lensing data. And the values converge on Lambda Cdm. Okay. The RSD, as I showed in the last slide, are not that sensitive to curvature yet. Okay. The difference between gray and blue is not that significant. So when you add the RSD to the CMB, you don't get a very tight constraint. On the other hand, on the right-hand side, the equation state for dark energy, you do get that sensitivity now from RSD. So going from gray to blue is where all the information is coming from. Adding in the weak lensing again doesn't actually offer that much. So the two nice complements. Weak lensing a nice complement for curvature. RSD is a nice complement for W. And they both allow you to take the uncertain models of the CMB only without anything additional and shrink it down to a Lambda Cdm preferred model. Okay, so growth also gives you the same conclusion that Lambda Cdm is preferred. You can look at sigma 8, and what we find is everything lines up with Lambda Cdm predictions from Planck. Okay. We also can test, now that you have weak lensing and RSD, weak lensing tells you is a relationship between photons, which are massless, and gravitational potentials. RSD is taking massive particles and putting them into gravitational potentials and measuring the effect. So you can actually disentangle the Poisson equations in general relativity into the contribution from massive particles, which I show on the top, and from massless particles, which I show on the bottom. And you can parameterize perturbations to these GR equations that are just simple first order changes as a null test on GR. And you can do a null test on the massive component, and you can do a null test on the massless component. The parameters for doing so are mu naught on the massive component and sigma naught on the massless component. RSD are only sensitive to the massive component. That's the blue curves. Weak lensing are almost entirely, not completely, but mostly sensitive to the massless component. They're very perpendicular to each other when you look at these in combination, and you get really nice constraints, again, that say the Poisson equations look like they're what they should be according to general relativity. We prefer no perturbation to general relativity, either the massive contribution or the massless contribution. 0 is the preferred value in both cases. So it's a nice null test on GR. Okay, I'm going to skip the neutrino mass stuff. The bottom line here is that we can get constraints of 95% upper limits around 100 millielectron volts, which is on the border of differentiating the normal hierarchy and the inverted hierarchy for neutrino masses. It's if we can get another factor of 2, we can then start differentiating those two regimes. But we're doing fantastically well on the neutrino mass estimates. And also, most of the information is coming from Planck and BAO, this first red panel. That's the other thing we learned. The growth measurements are not yet giving us as much sensitivity to neutrino mass. Okay, so let's wrap up with what I see as a legacy. What did we learn as we went from stage 2 to stage 3? First of all, the stage 3 experiments, at least the BAO and RSD side, there's no funny behavior. The distribution of BAO measurements, the distribution of RSD measurements, all scatters about the Lambda Cdm predictions, as you would expect given the error bars we're reporting. Okay. When you now treat the whole sample from BAO and RSD, you see that the SDSS data alone here in blue, those are the BAO and RSD measurements, really do line up with Planck and sigma 8 omega matter. Again, they really do line up with H naught, same story. The DES weak lensing and 3 by 2 point measurements are also consistent, but there's more degeneracies in those. Okay? There's no supernova in those DES measurements, which is part of the reason for those degeneracies. Okay. When you now take the supernova, in addition to BAO and RSD, you can open up a very, very wide cosmological model. You can allow dark energy to float in its equation state in both a constant term and a time varying term, and you can allow curvature to float. And that's this parameter space, omega k WWA, okay? The red is the contours from supernova plus CMB. The blue is the contours of CMB plus BAO and RSD. You can see they're largely perpendicular to each other. That's because the blue, they're giving you more sensitivity to curvature, as we showed earlier on. Whereas the supernova, when you combine them with CMB, they give you more sensitivity to dark energy equation state. They're very nicely complementary to each other. And when you combine them all, you get nice constraints on all three parameters consistent with Lambda Cdm. The figure of merit, which is the area of this curve here, the W naught WA curve, it's the area of this gray curve. That's 103. The smaller the area, the higher the figure of merit. So it's actually 1 over the area. What was predicted back in like 2005 is that when we concluded stage 3, the area in this curve would be about 150. We're at 103 and we haven't even used the supernova. We haven't used the final 5-year DES measurements for stage 3. So we're already 2/3 of the way there at the end of stage 3. Okay, so super impressive and following the long roadmap that was laid out 15 years ago. A lot of detail here. What I think is super cool in this figure or in this table is that you have all of the probes now, and each row is a different model. It's a different number of allowed free parameters. The first 3 terms, omega lambda, H naught, and sigma 8, those are my Lambda Cdm terms. Okay. If I open up the cosmological model, I look at the central value on omega lambda, and it barely budges. I flow all different extensions in, and the central value doesn't change. H naught, I throw in all these different extensions, 60, and the central value doesn't change. They're very, very small fluctuations. Sigma 8, no change in the central value. You also look at the error bars. These data are now so constraining that in all 3 of these cases, omega lambda, H naught, and sigma 8, the 3 key lambda CD parameters, no matter how flexible you allow your cosmological model, you're still at the 1% level in constraining those 3 parameters. It's totally amazing. Okay. And then the extension parameters are all consistent with Lambda CDM predictions. The error bars actually don't change very much on those parameters either when you add new free parameters. It's totally amazing. You look at the whole space now, and we compare where we are now to where we were 10 years ago at the end of stage 2. So stage 2 was, instead of the Planck telescope, it was the WMAP CMB experiment. It was an older supernova sample, and it was a small set of BAO measurements, okay? We call that stage 2. Stage 3 is what I showed on the last slide. It's the most recent supernova measurements. It's the DES year 1 3x2 measurements. It's all BAO and RSD from Sloan and Planck, okay? So what happens? Here in blue is the constraint on each of these parameters in the cosmological model when I just have the stage 2 measurements, okay? If I add in the SDSS only, so it's just stage 2 plus all the things we did in BAO and RSD, we get a significant decrease in the error bars. If you look at the whole posterior volume, it decreases by a factor of 40 when you add in SDSS data. Just forgetting Planck, forgetting supernova, forgetting everything else, just going from stage 2 to stage 2 plus Sloan. Okay, a factor of 40 decrease in the posterior volume. If I then add in, and additionally, the newest supernova sample, Pantheon, plus the DES data, plus Planck, I get another factor of 25 improvement. So I go a factor of 40 by adding Sloan. I get a factor of 25 in addition to that by adding Planck, new supernova plus DES. So it's a factor of 1,000 improvement over 10 years in this cosmological parameter space. We've shrunk the volume of uncertainty down by a factor of 1,000. That's a factor of 4 per parameter. And you see that's the red curves on each of these parameters here. If you also look more closely, you see that the SDSS really has the biggest difference in things like omega curvature, right, going from blue to yellow here, and H naught going from blue to yellow. So pretty impressive. Here, I will provide my summary slide. Really, with the conclusion of EBOS and our final measurements that I've reported here today, we wrap up the stage 3 dark energy experiments. That was the period from 2010 to 2020. Okay. It was focused on BAO measurements with 11 billion years of cosmic history, cosmic lookback time, and RSD measurements to a range of 1.5. There's lots of nice complements. The BAO offer higher constraining power and isolation, but really they complement the supernova because of their power is in a different redshift range. They allow, I think one thing that's lost, I really want to hammer home again here in this talk, is that they allow really robust estimates of H naught. In terms of the measurement, they're really not possible otherwise. Okay, when you say H naught is 68 from CMB, you need the BAO to say that with real confidence. Okay, otherwise you don't have enough understanding of the expansion history and the other independent constraints. Okay, RSD not yet. Growth of structure measurement is not yet as constraining as distance probe measurements. However, with RSD plus weak lensing, we still favor Lambda CDM independently of the expansion history. Okay, that's super impressive. They also independently support general relativity because they both line up and indicate no changes to the bosonic regions. The largest role in improving the neutrino mass constraints really comes from SDSS BAO measurements. The 1 sigma error bars are about 60 millielectron volts, which is comparable to the minimum allowed mass from neutrino oscillation experiments. And lastly, you throw all the data together in a can, and it really does prefer the Lambda CDM model. I would really say the most constraining power at least in the parameter space we chose here today. We didn't choose things like the tilt of the power spectrum, but in this parameter space, it's really the BAO and RSD measurements that have had the highest impact in constraining the cosmological model. So I'll wrap up on that last statement. I'll remind everybody that this was a great program from the Sloan with sponsorship from the Sloan Foundation, partner institutions, DOE, and I'm happy to take questions here.
Okay, thank you very much for the very impressive talk. We have time for questions. If you joined us on YouTube, please put your question in the comment section. And if you join us here on YouTube, on Zoom, please raise your hand and ask your questions. Luis, go ahead.
Can I go first because I have to leave in a couple of minutes? First of all, Kyle, extremely impressive. I think it was the most interesting wrap-up of stage 3 that I have heard. All this material in the papers, or that's your own wrap-up?
Yeah, okay. So if you read the summary interpretation, it's a phenomenally beautiful paper.
Okay, I don't have to.
And this is all taken from that paper. And
I
it's
don't
really,
have to read the 23 papers. I just read
no,
one.
no, just one. One paper.
Right.
No, one paper. It's the EBOS collaboration paper.
Okay.
That's the final interpretation results.
Okay.
You can access it from the wiki from our not our wiki pages, from our EBOS web pages.
Well, will do. I know how to find it.
Okay.
The other thing, Kyle, is that I think I have to congratulate the whole area, because I think the contribution that you guys have given in terms of the figure of merit, I always wondered how precise those guesses that people did, that the panel would work out, because there were so many assumptions. It's just unbelievable, the numbers that you get. I mean, this is really top notch, and I think this is a fantastic position that puts the area for the future. And saying that, I mean, I mean, what will DESI do? Stage 4.
Yep.
Will there be a stage 5, or is the end of science?
Okay, so those are huge questions that we're actually working on right now. Okay, so question number 1, what will DESI do? So we're actually writing up the cosmological forecasts literally right now. The chains are running for DESI.
Yeah.
And that paper will be out. It's again, it's going to be an alphabetical paper. I'm largely writing it. That will be out in the next couple of months. And if we take conservative estimates from DESI, just like simple measurements of RSD and BAO measurements, the figure of merit is going to be, I think, around 300. So it's going to be more than what was promised to go from stage 2 to stage 4. Okay, so it's going to be that's conservative. That doesn't take into account things like measuring RSD on smaller scales. It doesn't take into account measuring things like full shape of the power spectrum, or getting actually extracting information from the wiggles, like omega matter. So we should do well in DESI, and there's no reason to believe. I think one thing we see in stage 3 is we're well below the systematics limit, or the systematics limit's well below the statistical limit. So that should hold true for DESI as well. So I think the forecasts in a conservative sense are very trustworthy in DESI. And my goal in DESI is what we're pushing forward. You know, a spokesperson, we try to drive the analyses in certain directions. We want to drive things past the baseline goals. We want to get more than just the BA and RST techniques that we did in EBOS. So DESI should at a minimum do what it's promised, but hopefully much more. That's the first part of your question. The second part of your question is, okay, stage 4 is DESI. What is stage 5? So I'm writing next week, you'll see papers that start answering that question. We're in the SNOMAS process in the United States, where we're trying to identify science drivers and observational programs for basically for the 2030s. It's harder. There's no longer a dark energy task force figure of merit to guide us. You now have to look for whole other ideas. So that's one of the reasons I wanted to choose this other figure of merit, which is the whole posterior volume over all cosmological parameters. Mm-hmm. So that's a factor of 1,000. That looks a lot better than the figure of merit of just dark energy. It also is more holistic. It allows other things to consider. You can start throwing other things in there like modified gravity, inflationary physics. And I think that's the direction we have to go to stage 5, is think about more holistically beyond just dark energy. But we have to think about comprehensive tests of the cosmological model using super high fidelity samples. That's the paper I'm writing. Get number densities that are like 10 times higher than DESI, and really do a thorough test to see if the clustering abides by the cosmological model on all scales. Okay.
Wouldn't you be going also for CMB more and more?
CMB, the direction is so
because at the end of the day, you have to figure out about inflation, right? And as far as CMB is the tool that we have, right?
Well, no, yes and no. CMB is the tool for measuring the tensor scalar ratio. So for particularly getting gravitational waves. And absolutely, so the big experiment going on in the South Pole to do that measurement. But there's more inflation than the gravitational wave component. There's also questions, like how many fields there are, and they will introduce non-Gaussianities in the matter fluctuations. And you have many more modes in spectroscopic surveys to look for those non-Gaussianities than you do in the CMB. So that's a direction that we're also advertising to go in with future spectroscopic surveys. And there, the volume comes at redshifts 1 and higher. You can't get the large number densities, but you get huge, huge volumes. Mm-hmm. So we're looking at new spectroscopic samples of tens of millions of objects between redshift 2 and 5.
So that would be the super duper DESI, is that it?
You need, realistically speaking, we're arguing, you need at least a factor of 10 more powerful than DESI.
So 8-meter telescope with 10,000 fibers, is that it?
That's something of that scale. So there's 3 facilities. That's right, Louise. There's 3 facilities of that scale that are being proposed. The first is called MegaMapper. It's a 6.5-meter telescope like the Magellan with 20,000 fibers on it. The second and that's coming out of LBL and Carnegie. The second is called Mauna Kea Spectroscopic Explorer. That's coming out of the Canada, France, Hawaii collaboration. That's like a 12-meter telescope with 20,000 fibers on it on Mauna Kea. So it doesn't have overlap with LSST as much as one would like. And the third is called SPECTEL, and that's the one I'm the most excited about, but it's also the furthest behind of three concepts. And that's a European Southern Observatory facility that's in Chile. So it overlaps LSST, and it would be something of the scale of Mauna Kea Spectroscopic Explorer. It actually has the potential to be up to 60,000 fibers on a 12-meter telescope.
Okay, that's
100.
I'm going to retire. I'm going to retire.
Yeah, but this is 2030s now. And in that scale, SPECTEL with 60,000 fibers is 100 times as powerful as DESI.
Oh my God. Okay, my last comment. Please come back and give us an update on SNOMES. That would be great, okay?
Yeah, you know who you can also ask? You can ask one of the SNOMES conveners. I'm not a convener. You can ask Andrzej Slazar. Andrzej would do a fantastic job.
Okay, we'll do that.
You know him, I assume, right?
Yeah. I know him.
So my recommendation is to ask Andrzej. He would do a great job.
Okay, look, thank you very much, and let other people ask their questions. Thanks a lot. I gotta go. Bye-bye.
Thank you, Luis. More questions? Well, while we wait for more questions, I have a very basic questions from someone very outside the cosmology world. With such parameter, good measurements for these parameters, is there any reasons to expect new cosmologies or new models? Yes.
Okay, so that's really your question is like, well, you should have a whole talk on your question. Okay, and it's really specifically in this regime here. I'm sorry, right here. Okay, you should ask for someone to give a talk on this topic, and this is the H-naught tension. So no matter how you look at it, you get very different measurements between H-naught if you look at the early universe model or the late universe model, right? Just direct, right? Supernova, all you do is you get a ruler, okay? And you go and put it on, you calibrate it here today, and you look at things further away and you see what's the distance of that ruler compared to the expansion, compared to the rate that things are expanding. So it's a ruler and kilometers per second, the two measurements you make, right? And you get H-naught. It's no physics. It's just simple arguments. So the only way for that to be wrong is if you have dust or some annoying thing that has caused you to miscalibrate the ruler. But the underlying physics are not wrong, okay? Now, the other technique is underlying physics. It's okay, what happens the first 300,000 years of the universe? How do you set the ruler we use in the other technique? So the other technique, instead of building your ruler here on Earth, you build it in the first 300,000 years of the universe, theoretically. You know its length, and then you have that as a tool to measure velocity in one dimension and the length of the ruler in the other, and you get H-naught, right? Same idea. So there's no way the measurements are wrong, okay? In the supernova case, maybe the measurements are wrong, but the physics are right. Okay, in the other case, this is the key point here. There's no way the measurements are wrong. That's what this plot is showing. No matter what you do, no matter how you turn the knobs or throw data out or throw data in, you get the same answer. Okay, it's 68. So if the measurements aren't wrong, that means the only possibility is that the physics are wrong. And that would be groundbreaking. That's like a Nobel Prize, right? Because then you've discovered that there's some new particle or some new interaction or some new field that existed in the universe 300,000 years after the Big Bang that affected the shape of this ruler that I don't have in my universe today. or I don't know about in my cosmological model or my particle physics model. And that would be awesome. That's what everyone is hoping. But it's not so easy. It really, you know, because once you start changing, once you introduce a new field, it can change other things. It can change the shape of your power spectrum that's measured in the cosmology background. It can change this, it can change that. So you have to be very delicate. You have to be able to introduce some new particle in the early universe and not have it affect anything except for this prediction for R sub D. So but you have the whole talk on that would be worthwhile. It's that probably is the biggest new direction in cosmology. But the other reality is we're not going to do much better with BAO and CMB because we're already doing so damn good. Look at this. We're in this table, we're already measuring it at the 1% level. That's the whole problem. All these first 4 entries, or the first 3 entries, that's consistent measurements in using CMB and BAO. It's all 1%. The tension comes down here, right? Like look at this distance ladder, 74 plus or minus 1.4. It's a much larger error bar. It's twice the error bar. You have to improve those measurements to really see if the tension's real. And you also see that different techniques come up with slightly different results. Like the tip of the red giant branch here, that tells you it's 70. That's a low redshift direct measurement that disagrees with this. So I think all the action has to take place in low redshift now using simple geometric arguments and see if the low redshift measurements are 68 or 74. But if everything comes out to be 74 using low redshift, it means there's some new physics. We've discovered a new extension to the particle physics model, the standard model for particle physics. That's awesome.
Okay. Yeah, that's awesome. Brilliant. Thank you. Thank you very much.
Okay. Well,
more questions?
There's no more questions.
Okay. Well,
okay.
If there are no more questions, let me first thank you everyone for attending and saying that this presentation will be available on our website and on LIneA's YouTube channel. And I'd like to especially thank you, Dr. Dawson. Thank you for taking your time, for being with us today and giving this amazing presentation.
Okay, well, thank you so much, everybody, for joining us. And I'll send you the PowerPoint slides shortly.
Okay, thank you very much, everyone.
Yep.
Have a great day, stay safe, and I hope to see you all again in our next webinar next Thursday. Thank you very much.
Bye, everybody.
Bye-bye.